Okay, so we'll go ahead and get started. I'd like to welcome everybody today to our College of Natural Sciences webinar series. My name is Allison Sherwood. I'm the Interim Associate Dean for the college. Through our Pilina webinar series, we are hoping to spread all the wonderful research that happens within the College of Natural Sciences to the broader community, as well as some of the research that happens with our college and sister units on campus here at the University of Hawaii at Manoa. And so today I have Dr. Shadia Habbal, who is from the Institute for Astronomy, where she is an astronomer and the graduate chair, also here on the Manoa campus, and she's going to be sharing some of her research with us today. Dr. Habbal specializes in the study of the origin and the evolution of the solar wind, the stream of protons, electrons, alpha particles, and traces of ionized heavier elements that flow outward from the sun. The solar wind shapes the tails of comets, creates the auroras seen near Earth's polar regions, and alters the magnetic environments of planets in the solar system. She also studies the enigmatic solar magnetic field, which seems responsible for many things, including extremely high energy phenomena such as solar flares. She receives major research grants from the National Science Foundation, as well as NASA, to pursue the study of the solar corona, which can only be seen from Earth during a total solar eclipse. She's been doing total solar eclipse research for the past 25 years. She's the principal investigator of her research group, which is called the Solar Wind Sherpas. And so at this point, I'd like to turn our time over to Dr. Shadia Habbal for her presentation. Welcome.
Thank you very much for the introduction. Thank you for having me, and welcome everyone. So I'd like to start by sharing my screen. And okay, so what I'd like to share with you today is unique research with the Solar Wind Sherpas, who's composed of different contributing members from all over the world. They have joined different stages of since I started this research direction, and they have all joined for their love of scientific adventure. So this background image was taken during the 2017 total solar eclipse that swept across North America. When you see a total solar eclipse, that's not exactly what your eye sees, but the image has been processed to bring out all the incredible fine details that we see in the corona. So I'd like to start with I thought of the quote from The Little Prince from Saint-Exupéry. And then he says in French, on ne voit bien qu'avec le cœur, l'essentiel est invisible pour les yeux. And in English, it's one only sees clearly with the heart, the essential is invisible to the eyes. This talk is rather, we can only see the glory of the sun with total solar eclipses, the essential is invisible to the eyes. And this is what I will focus on today. So very quickly, just for those of you who are not familiar with how the clockwork of planetary motions work, well, you all know that the moon orbits the Earth, and the Earth moon orbit the sun, and but it just so happened by some fortuitous coincidence, or whatever you want to call it, that the angular extent of the moon is the same as the sun when seen from Earth, and it's once every 12 to 18 months, the alignment between them is such that if the moon intercepts the sun, then it will cast a shadow on the Earth. And this is when you can see the outer atmosphere of the sun. So it's only in a band on the Earth that's about 100 to maybe 150 kilometers wide, with a duration of anywhere from a few seconds to a maximum of 7 minutes, can you actually see the extended atmosphere of the sun, which is the solar corona. So this is a sequence of how this occultation occurs. It takes about 2 hours from the beginning when the moon starts to cover the solar disk, and so you have the partial phases. At totality, when everything is totally covered, and you really have to have all the solar disk covered, because it's 1 million times brighter than this outer atmosphere. And the maximum duration of this phase is only 7 minutes at best. And then the moon recedes and the bright sun comes out and the corona is gone. And this is an animation, or it's actually produced by Goddard, by scientists at Goddard. Let's see if I can. Okay, so it's showing you how the shadow band covered the US in 2017. And it's really the red band in the center is where people could observe a total solar eclipse. Anywhere else, you could only see the partial phases, and therefore the corona couldn't be seen. So one has to really know where they're going, to know exactly where the location is, to be able to witness this beautiful phenomena. Okay, this is a picture taken by Judd Johnson, who's in the audience today, and it was taken from Argentina in Rodeo, a small village, I would say, in 2019, in July 2019. And here in this image, so of course, with a little camera, I think he took it with an iPhone, you don't see many details of the corona, but you do see that the disk of the sun is dark. And the beauty about this picture is you actually see the extent of the shadow band in the sky. So just to go back a little bit in time, just to give you a flavor for how, how people perceive total solar eclipses and how they even realized that what they were. So the first recorded observation of the corona during a total solar eclipse appeared on oracle bones in China. And the inscription said, 3 flames ate up the sun and the great star was visible. So I should add that during a total solar eclipse, the sky is darkened to something comparable to twilight, or even a little darker, depending on the conditions. And you can see stars during totality. So it's like seeing the night sky in the daytime. Now, the oldest record of a verifiable solar eclipse appeared on a clay tablet. It was discovered on a clay tablet in Ugarit in northern Syria in 1223 BC. This Assyrian tablet shows that the Assyrians actually, they list it's in a great treatise of astrology, and it shows that they actually knew how to predict eclipses. And that's thanks to the discovery of what we call 18-year cycle, which is the alignment of the sun, the moon, and the earth kind of recurs in a same pattern every 18 years, because the plane of the orbit of all three is not always is not the same. So you have to have this perfect match, and this identical configuration occurs every 18 years. This is from ancient China. So of course people also feared these events, because if you didn't know what was happening and all of a sudden the sky went dark, it started to dim, and all of a sudden you were at nighttime, you really didn't know what was going to happen next. So in ancient China, for example, they considered eclipses to be frightful and abnormal, and they were thought to be caused by a dragon that tried to devour the sun. This is another interesting event. This was in the 6th century BC, where there were 2 clashing kingdoms, and they were at war for their frontiers. That's nothing new, I guess, throughout the history of mankind. And a total solar eclipse happened during the battle. And so they basically interrupted the conflict, and it led the 2 kings to agree to a peace treaty, because they thought this was an omen from the gods that something terrible would happen if they continue. So now moving on to just sharing with you what is so unique about the scientific contributions of the total solar eclipses. These are, so before the advent of photography, people would observe an eclipse, and they would have actually in their team people who would sketch what they would see with the eye. So one example is given here from 1878. So you see there are very, very fine rays everywhere. Some of them have, you have some shapes of kind of converging arches, and the solar physicists call them streamers. In addition here, there was something very interesting that was recorded, this kind of reddish appearances around the disk of the sun. And these are called prominences because they're prominent around the disk of the sun. And although they're in volume-wise or space-wise, they occupy such a small space, I will show you how important they are for what happens also on Earth. The one on the right is one of the early plates from that were taken during a total solar eclipse. So you can see this is with photography here. The difference between the two is that the eye was on the left was able to capture exquisite fine details. On the right, you have to choose your exposure time so just right so that you can see all these fine rays. And because of the dynamic range of the corona and the emission from the corona, what people do, and nowadays and even before, you take a series of exposure times to be able to cover all the way from the solar surface all the way out to several solar radii. And the example I started with was precisely from that kind of procedure. This one is very special, and I will get back to it later in my talk. As you can see, you have these very, very fine rays that are everywhere in the corona. And then all of a sudden you have this little swirl at this edge of the sun. Again, I should note that these are the prominences that were drawn in pink in the earlier example. So I will come back to this one. So at the time, people thought, well, this was maybe a fiction of the imagination, and they didn't pay much attention to this particular structure. So if we want to explore, first of all, what's the origin of these structures? What are they telling us about the corona? What is the corona made of, etc.? And also, what we see with the eye is you see a certain span of these rays out to a certain distance from the sun. And the question is, how far do they extend? So to do that, we have to go back to the solar disk that we actually need to cover during a total solar eclipse and try to figure out what's going on the solar disk. These are two examples These are two examples taken at different times. One is 2001 on the left and 2018 on the right. And you can see that the big difference between the two is here you have appearances of these blotches, or what we call sunspots, on the surface of the sun. And here there's practically nothing except this very, very small region. So clearly something is happening on the surface of the sun, and actually the Chinese had a very, very long extended record of observing sunspots and recording their location. Of course, to do that, you have to use special protection for your eyes, like welder's glasses or something, smoked glasses. And Galileo used the observations of sunspot to confirm that actually the sun was rotating, because as the sun rotates, the sunspots will change position. So in this example, they would have appeared earlier on the east side of the sun, and now they're more towards the west. Okay, so the origin, or really the nature of sunspots, was discovered by George Ellery Hale. He was an avid solar observer, and it was soon after the discovery of the Zeeman effect that he thought, well, gee, the details around the sunspot look like iron filing when you have them next to some very strong magnet. And so he knew from that Zeeman that from spectroscopic point of view, if you put the slit of your spectrometer, you can see a split in the spectral lines. And sure enough, the first time he reported it in 1905, he had something like this, where you see, instead of having just one spectral line, you have three. And from the separation between these three components, you can tell what the strength of the magnetic field. So that was the discovery, that sunspots are the locus of very strong magnetic fields on the sun. So one has to recognize that this was an incredible discovery with significant impact for the future, for astronomy and the future. And again, as I mentioned earlier, we would wonder, like, okay, magnetism, we can see it on the surface of the sun, but how far does it extend from the sun? Now, in addition to this observation, there were other observations of looking for long records of sunspots, and the realization that the sunspots, the numbers varied as a function of time. A given cycle is about anywhere from 11 to 12 years, or 10 to 12 or 13 years. And each cycle doesn't always have the same numbers. So on this axis is the number of sunspots that appear. So you see sometimes you can reach a maximum of 250, and at other times the maximum is barely 50. Now, in addition, there was a time period when the sunspots were practically non-existent on the surface, or they couldn't be detected. And this is now called the Maunder minimum, because although it really should be attributed to a German pharmacist who was called Spörer, who was the first to report it, but Maunder was the one who actually made extensive publications around this minimum. So the question is there evidence in the eclipse observations of this variation of the sunspot cycle? Because just to remind you, the sunspots are observed on the surface, and the coronal emission is showing things extending further away from the sun. So the question is there any correlation between the two? And do we see this, the impact of the sunspot cycle in the eclipse images? These are two examples from 2013 and 2019. You can see that the corona has changed significantly between these two times. Here it was when the number of sunspots on the surface of the sun was at a maximum, and you can see how it's almost the corona is almost vibrant. You could almost feel that it's telling you something is happening. And things are happening all around the sun, and these pink features are the prominences I mentioned earlier. In 2019, you can see that things looked very, very different. But what was really very interesting is right in this region here, you can see that, that there's a lot of turbulent structures. It's almost like you have waves overturning in the corona. And I'll show you more examples about this. So here you have some wavy patterns, you have features like this, and I'd like you to just remember this structure here that we will get back to in a little bit. This is a compilation that was made by my, at the time, student Ben Bo, and taking all the white light images, the high quality white light images that were processed by Miloslav Druckmüller, and he compiled them with the black being the brightest and the white being the darkest, just it was better to showcase the features on the sun. So it goes from 2001 all the way to 2019. I've indicated when solar maximum is, so that was the first maximum. The second maximum was in 2012, 2013. So that's about 11 years difference between them. And then in between you have solar minimum at 2009 and the solar minimum again at 2019. So you can see that the corona looks more or less the same, similar, I should say, at solar minimum, and at maximum, it's just very, very complex and actually much more exciting to look at than solar minimum. Okay, so now, in addition to these images that were taken in what we call white light, so it's basically the light that the eyes are seeing naturally. And I will explain later from a physics point of view what this light is coming from. So now I'd like to move on to something we call the colors of the corona. And this is what we can do if we use spectroscopy And we use the fact that, there's more in the images than just white light. So this also arose from an observation in 1869, which was really fundamental, in the sense that Young and Harkness took a spectrum of the corona during the eclipse. It's this little spectrum, so they just see the colors almost like the rainbow split into the different colors. So each one, a color is around the solar disk, and they couldn't identify this particular color, so they called it coronium, what appeared to be dominated by green. They couldn't identify it in the sense they didn't know its wavelength. They couldn't associate the wavelength they were seeing with any emission from an element or ionized element on Earth that which were known. So they gave it the name coronium since it came from the sun. Now this is in 1869, and it wasn't until 1941, so almost 70 years later, that two scientists, Edlin and Grotrian, identified it as iron, the element iron, that had been stripped of 13 of its electrons. So to strip an atom of 13 electrons, you have to have a temperature of at least 2 million degrees. So the implications were really significant. One is nobody ever expected the outer atmosphere of the sun or any star to be much hotter than the surface. We know that there's fusion going on inside the sun, and the temperature is about 10 million degrees, and it drops to about 6,000 at the surface. So what is causing this temperature all of a sudden to rise to over 1 million degrees? Now, so this was the first consequence. The second consequence of this discovery was that the gas in the corona cannot be neutral. It's not like the gas you find around you, the air we find around us. It's fully ionized. And then in 1958, Parker came up with his theory, and he showed that this atmosphere at such a temperature couldn't remain bound to the sun despite gravity, and that it was going to end up expanding supersonically, and he called this expansion the solar wind. And soon after, with the beginning of the space exploration, the existence of the solar wind was confirmed by spacecraft that were in interplanetary space. They had instruments to collect like particle detectors, and they actually measured a flow. They measured particles traveling at a certain speed. Now, the other very important implication of the fact that the corona is very hot at these temperatures of over 1 million degrees is that the surface of the sun is cool, it's 6,000. So you can actually observe the corona, both the solar disk, the projection on the disk, and its extension with X-rays and ultraviolet. And you don't have to wait for an eclipse. But to observe the sun this way, you have to go to space. So you can just remind yourself that this 1869 was really the seminal discovery, and the 1941 work by Edlin and Grotrian that led to basically an explosion in our space exploration, not just for the sun, but for the stars as well. And this is this is just an artist's rendition of what the solar wind would look like. It's just those streams of particles that are just flowing away from escaping from the sun. Now, this is the actual data. These are the actual data that were collected by the Mariner 1 spacecraft in 1963, which confirmed the existence of the solar wind. I know it's not ideal because what's plotted is one of the curves is the speed of the particles they detected. The other one is the density. And so what they observed is that, first of all, the speed varied between 300 and 800 kilometers per second, which is almost equivalent to 1 million kilometers per hour. So this is way beyond what we experience, anywhere in our everyday life. So you have these streams of particles, just spewing away from the sun at this speed. And what they observed is that the speed was really controlled between these two limits. They haven't since then, we haven't detected anything much smaller or much higher, but I'll explain under which conditions. The other important finding was that you have these recurrence of fast streams, so when the speed goes up quite a bit, but also that the density or the number of particles per cubic centimeter was anti-correlated with the speed. So whenever the speed was low, the density was high, and vice versa. Now, the evidence of the solar wind also resides in the ionized tails of comets. And many people had thought about the fact that there could be this, what they call corpuscular flow from the sun, until Parker came up with a theory, because from just observations of comet tails. So the comets, under very good observing conditions, you can see two tails. One is a dust tail, and the dust tail just goes, it's just dragged by the motion of the comet around the sun. The ionized tail, on the other hand, is always pointing radially away from the sun. And now we know that this is so because it's ionized particles arising from the sublimation and ionization of cometary nucleus material. And then these ions, and now we know one of the properties of the magnetic field is that an ionized particle or a charged particle will latch onto a magnetic field line and gyrate around it and just also be taken, transported with it. So from now on, we know that all these traces here are really tracing the magnetic field lines in the solar wind. And the same is applicable to the Earth's aurora. So the aurora is always there. Sometimes it gets to be much more intense than other times. And it's really the penetration of particles from the solar wind into the upper atmosphere of the Earth and ionizing oxygen and nitrogen. Ionizing oxygen and nitrogen, and these curtains of emission actually follow the magnetic field lines of the Earth. So it's not the magnetic field lines of the sun, but they just latch onto the magnetic field lines of the Earth. Okay, so I don't know if anybody wants to ask a question, or we wait till the end. So I'd like to now move on to the space age. So you might wonder, well, now that we can observe the sun in X-rays and extreme ultraviolet, not just anything beyond its edges, but also its surface, the corona projected against its surface. Why do we bother with total solar eclipse observations anymore? And I want to show you how these are still remain they still provide very, very unique pieces of scientific information. So this, I don't know why it's doing this. Okay. This is a composite from different colors in the ultraviolet spectrum that are taken from space, and they're combined together to produce this picture. So this gives you an idea of how the corona looks like in the ultraviolet, extreme ultraviolet. And what you see is, it's obviously a beautiful picture, but what's interesting is that it's not cut off by design so close to the sun. It is actually a fact. The extreme ultraviolet is produced by excitation of elements, but it's also by collisions with electrons. And so how far the intensity goes away from the sun depends on the product of the density of the electrons and the density of the ions that are producing this emission. So we know that just if you take pure gravity, everything drops off as 1/r². And here you have at least a 1/r4 dependence. So the intensity drops very, very quickly. The difference, and I'll explain it later, with the visible is that it only depends on the number density of the ions. So it's not a density square effect. Therefore, you can see the emission much further away from the sun, and this is critical. This is a combination of two types of instruments from space. The one is the one I just described, the one at the center. The one around it is mimicking an eclipse, where you put a blocker in front in your optics so that you cover the disk of the sun. And what you see around it is the extension of the corona in space. But again, this is what I refer to as white light. So this one doesn't have any information about the ions. It's just produced by the electrons that are streaming away from the sun. And I forgot to mention that the solar wind is dominated by an equal number of electrons, protons, some alpha particles, and a very, very, very minute number of heavier elements. Remember, the first discovery of a spectrum of the corona was from iron. So clearly iron is there, and there are other elements too. So here what I have done is the images from space were all taken at the same time as this eclipse in 2012. And I superimposed the eclipse image just to show you that if you started with this one, you would have no clue as to how these structures here connected to their source at the sun or where they came from. But the moment you add the eclipse image, oops, what happened? Oh, then you can see the intricate details of what we call the inner corona and how they end up evolving and expanding into outer space. So all this complexity close to the sun kind of disappears and just flows outwards into space. And this is a composite from the middle. The central picture is from, again, this extreme ultraviolet imager from space, and the outer one is from the eclipse of 2010. And you can see that there are some beautifully intricate features here. But the beauty of this example is to show you the details that are obtained from space compared to also with a camera, with a Nikon camera from the ground. There is the intricacy of the corona is present in both. So this by itself tells you, one, this is the extent of the extreme ultraviolet. Clearly, it's cutting off too close to the sun. And the other is that the eclipse observations have the same quality, the same spatial resolution to show us, to indicate how all this expansion is happening. And of course, all these intricate features everywhere in the corona and on the surface of the sun are determined, we know now, by the magnetism that's produced below the visible surface of the sun. So magnetism plays a critical role in producing these structures in the corona, and it's also how it evolves and changes as a function of time. So now I'd like to share with you, all these were still images. They were like in instantaneous, you capture the instantaneous state of the corona. And you also capture the instantaneous state of its dynamic evolution. So I'd like to share with you this. This is a movie that was made by our colleague Druckmüller, whereby he took the extreme ultraviolet observations from space and he combined them, and because their temporal cadence is 12 seconds. So you can imagine you take a movie over an extended period of time and you can see how the corona is evolving. So this is, I'm going to start the movie, and the most dramatic changes are happening in this region here. So I'd like you to follow here, to focus mostly on this region and see what happens. It starts very, very slowly. You don't practically see anything happening. And then all of a sudden, you see this huge explosion on the sun. I don't know if you noticed that there was a very, very faint envelope. And then some of the material keeps on escaping from the sun, and some of it falls back on the solar surface. And look what happens. It's like bomb falling on the surface, and you have this sudden flaring and brightening everywhere on the surface. So clearly the magnetic fields are not just sitting there idle, they are doing something, they are changing continuously. And the gas, kind of latched onto it is also changing in tandem. But what's interesting is this explosion that I showed you is happening from these prominences. And we now know that they are the coolest and the densest structures in the corona. And there aren't that many of them, but they seem to be the tail that is wagging the dog. Okay, so what do we know about prominences? This is a picture from one of the spectral emission from space. It's in a helium line, so it's formed at cooler temperature. It's about 10,000 degrees. And then you have these protrusions, which are the prominences. And the surface also has a lot of cool material. But then you don't know how these are connected to the corona, because from this space-based image, there is no information, the information is missing. But I should say that this image is taken during the eclipse of 2010. And this rectangle here is this one over here. And you can see how right away you can see the connectivity between, or at least you're filling the gap here, and your eye can see what's happening beyond the surface of the sun. And so all these different, you see that there are some very intricate details in the corona, and they are all driven and produced by these prominences. And it's only through these eclipse observations that we were able to discover this, because there is no other observation that shows you the connectivity between what's happening on the surface and how things move outwards. This is a higher resolution image, and you can see this very, very strange features within prominences that are very different from this more, very thinly linear structures in the corona that are either expand straight out from the sun, or they produce arches in the corona. I don't know what this, no, sorry, that's not what I wanted. Okay. And you see here, there is some connectivity between this emission from, which is from hydrogen, and the white light that's showing up in the image. So here, these kinds of observations really confirm the direct link between the prominences and all the overlying structures you see in the corona. So now going back to Temple, now we know that what he had found here, he had reported rather, was what we now call coronal mass ejections, which are produced when these prominences explode. So he saw it with the naked eye, and he recorded it, but at the time it was not known. So this is an example from space. The images have been processed slightly differently, so you can choose to focus on either one. They're both identical data. And you can see what we mean by when we say coronal mass ejections. You have these huge bubbles originating from the sun, but you can't see their origin because in this, the instrument has a big occulter, but you can see how they expand away from the sun. So you have two components to the solar wind, one which is the background solar wind streaming away from the sun. And in addition, you have these more dynamic explosive events. And these events are can be detrimental to our Earth-based satellites because they squish the magnetic field of the Earth, and they can cause huge disruptions. So one of the lines of research is to try to figure out what causes them. Second, can we predict them? Can we predict the ones that are going to be Earth bound so that we can protect our satellites? This example is from the eclipse of 2013, and I just I will run the movie, the movie here from the space-based data, and I want you to just notice this bubble which I had pointed out earlier, and this is one of the classic shape of a coronal mass ejection. Sorry, so this is going to start, whatever is in this white light image below the occulter, you can't tell. But because we have the eclipse image at one instant of time during the sequence, that you can tell exactly what happened. So let's look, mostly if you want, you can focus on the event at the bottom. So you have this front that's coming out of the sun, and it's evolving and evolving. And sure enough, this is exactly what this is. And if I stop it here, it's what was captured in the eclipse image. And the eclipse image has a much higher spatial resolution because of the camera that was used. But what you can tell then by comparison is that the structure here remains tethered to the sun, this tether here. So they expand into interplanetary space, but it's like an umbrella or a balloon that stays attached to the sun. These are other examples. I want to make sure I don't run too late. And so that shows you the intricacy and the incredible details in the corona, especially during solar maximum. So I won't, if you want, we can go back to them later, but okay, so this one, again, in addition to these large scale features, there are features very, very close to the sun, which we call plasma instabilities or turbulence. And they're, so they were never captured with this detail before, except in these eclipse observations. So one question is, what happens to these turbulent features or these vortices or plasmas? This is an example from the eclipse of 2020. The superposed on instead of the moon, we have an image from space in helium. And you can see that it is close to solar minimum or past solar minimum. But you can see that there was this very intricate coronal mass ejection, and Ben did a very nice study of it. But what I want to point out here is that now there's a spacecraft in getting very close to the sun, which is called the Parker Solar Orbiter. And they have an imager kind of similar to these white light images, except they look to the side. And what the imager detected after, past this eclipse is something similar, something like this. And you can see that the intricacy of what you observe in the corona remains, it doesn't change much as it's being transported far away from the sun into interplanetary space. So that means that all these dynamic events right at the sun are just go out into interplanetary space, and they have a signature, they have an imprint, and sometimes they can, be of importance that cannot be neglected. This is another example. They're not at the same time, but just to show you that these vortices, and we call them smoke rings in plasma physics, that they were seen also in interplanetary space. And so when they observed them with WHISPER, they didn't really know where they came from, but just comparing with what we know from the corona, from the eclipses, we know exactly their origin. So now let me move on to the colors of the corona. I'm not going to go into this slide, it's a little complex, but remember I told you that Young and Harkness discovered this coronium line. Now we know that the spectrum of the corona is very, very rich in all kinds of elements, ionized elements. That you have to keep in mind that all of them, because of the hot corona, cannot stay in a neutral state. And it just so happens that iron is the most dominant element, and it appears in different states of ionization, meaning that the temperature in the corona isn't uniform. It's not 2 million degrees everywhere. There are regions which are cooler and hotter. This is why we see all these different ionization states of iron, because the hotter the gas is, the more the electrons can escape from the atom. So what we do is in our observations, we have observed in all these lines, and now we found that really there are more or less two dominant temperature features in the corona. One around 1.2 million and the other around 1.8 to 2 million. So so what we do is we use filters with our cameras, and we can isolate the light from these ions, and we take images of the corona in this particular color. And from these colors, we can produce maps of the temperature in the corona. And we can also figure out the distribution of these different, what we call charge states. And it just so happens that in interplanetary space, there are instruments that actually can measure how many of these charge states are spewing out of the sun with the solar wind. And so we can, with our observations, make a direct connection between the origin of these ions in the corona and how they're detected into space, whether they change their identity or they remain the same. So this is an example. I showed it earlier. So this is the white light, and now I want to show you the different colors of the corona with our filters. So here we took iron 10. This is 1 million, 1.2. This is 1.4, and this is 1.8. So if you didn't know, you would look at these images. You would say, this is not at the same time because they look so different. It's actually taken at identically the same time during the same eclipse. So here, this is a direct evidence that the temperature in the corona or coronal structures have different temperatures. And what we're seeing is a superposition of all these different temperature structures. So here, what we've done is color-coded the different lines or colors so that you can actually, just to prove the fact that what's here in green is the very hot iron 14, and this is blue is the iron 11. And you can see that the two are not, don't coincide with each other. Should have removed this a long time ago. Okay, so this is a comparison of actually iron 10 and 11 that are very close in temperature, but yet you can see, you can distinguish between the two. And finally, least but not least, the turbulence that we saw in these images with these colors, we know that they are attributed to the very hot material, the hottest material in the corona, the iron 14 line. Okay, so this is just to recapitulate. This is how the corona appears in white light, and this is how it appears in two colors, the iron 10, which is red, and the iron 14, which is green. So now we can, establish a temperature marker to the structures we see in the corona. And finally, the prominences I told you about, we found from all our eclipse observations that they're always enshrouded by the hottest material in the corona. Remember, they are the coolest and the densest, and right around them are these hot shrouds. So it is no wonder that when they explode and expand, they're pushing all this hot gas ahead of them. And this is the hot gas that is forming the coronal mass ejections. Now, finally, from a scientific point of view, I want to tell you, I mentioned how we can now connect the corona to the solar wind by observing these, the emission from these iron ions. So this is a compilation from all the observations we have made starting from 2006 to 2019, where we also had observations from with these different filters of iron 11, iron 14. Now, the reason there are dates that are missing, because unfortunately, we are at the whim of weather. So sometimes in our observing site where we have the equipment that measures, that takes these images, we might be clouded out. So we often look to amateurs, they send us their images so that at least we know in white light what the corona looked like. And this is just showing you the number of sunspots throughout this whole period. So you can see that the corona changes a lot, as I mentioned earlier. Most important here is to look at the colors. So everything that's red is the cooler material, and it always seems to be spewing away from the sun. The green is the hottest material, and it seems to be the material that is more bound to the sun. So it's going to have a more difficult time escaping. And the only way it can escape is if you have the type of explosions I showed you earlier. Okay, so this is a little complicated, but it's important for me to describe it so that you can appreciate how the connection is made between the sources of the solar wind at the sun. So, as I said, there are instruments in space that measure the flow of particles and also their composition. So whether electrons, protons, and these very, very minute traces of heavy elements like iron. So the instrument ACE measures different ionization charge states of iron. And you can see what's interesting. This is throughout the whole year of 2006 at solar minimum, and this is the whole year of 2013 at solar maximum. So you can see that these charge states of iron fluctuate in this band. But what's interesting is that the average is around the charge state of 10. And this corresponds to our famous iron 11 line that we see in the corona. The other thing is occasionally you see very high charge states, and these are associated with coronal mass ejections. Now, the other thing I would like to point out is that whether we were at solar minimum or at solar maximum, you see exactly the same trend, that the dominant charge state is that of iron 10 plus, meaning iron that has been stripped of 10 electrons. Now, the other interesting measurement here is the speed of the wind. So this is how the speed of the wind changes as a function of time and at solar minimum and at solar maximum. And the color code is just for streams of under 400 kilometers per second are shown in blue, the ones 400 to 500 in red, and everything above 500 in green. So these same colors are transposed here in the charge state. So you can see that there are huge variations in the speed of the wind, but the charge state doesn't change. It hardly changes, except in these large events of coronal mass ejections. And this is really so. With this information, we now know that the steady solar wind streaming away from the sun is really coming from the corona, where you have mostly iron 11 emission. And this is summarized in this plot here. So all I'm showing is a picture, the colored picture, and this red emission is the iron 10 plus, which appears in interplanetary space. And this is the speed of the wind. Now, mind you, up till now, measuring the speed of the wind in the corona is very, very difficult measurement. Only one instrument was able to do it. It's no longer in operation. So with all our eclipse observations, we don't have any velocity measurements. We only have composition and temperature, and we can also infer the density of the ions and the electrons, etc. Okay, so I'd like to end by just giving you a flavor of what observations during total solar eclipses, how we do them. And I wrote here trials and tribulations because that's exactly the case. Usually astronomers, they go up to the telescope, they take their measurement and they come down and there you have your data. Well, we take our telescopes to basically wherever there is a total solar eclipse. So you can imagine that we always have to plan what we want to take with us. We're traveling, by air, by automobile, by ships. So the conditions for each eclipse have to be taken into account and slightly different. So here I'm writing the names of my collaborator, Judd Johnson, who's here today. I started with him in 1995, and people have accreted onto our group with time. The more senior members are Adi Dink, who's here and who's on Zoom, and Miloslav Drukmiller. And then I have a number of younger people who have come along over the years, and the most recent ones are listed here. This map is a map of the world, as you can see, and I've pointed with purple where we went to total solar eclipses. And the more curious one is Antarctica, which was this past December. So you can imagine for us here, well, we're now in Hawaii, but wherever. So this was 2017. I didn't put all the dates on them. But to go, it's not trivial to get to an eclipse. And of course, with COVID, it became even more difficult. Okay, so I will just show you a few pictures of our instrumentation. Everything is carried on board. We hardly ship things because we want to protect the equipment. These are the cameras which have the filters and take the colors of the corona. And these are our observing tents, which were designed by Judd, and they open up so that we can, observe the sun directly, but we're closed to protect the cameras and also to keep them cooled at a certain temperature. These are excerpts from Indonesia. You can see the amount of, we had 1 ton of luggage, and we traveled by all means of transportation. This is the team in 2017. We had 5 observing sites, and this is Antarctica. So this is where the eclipse was happening, and we were encouraged to go there, and the only way to get there was by being on board vessels. There was a tiny part of the land where they had 1 camp there, but it was they were charging $50,000 per person. So that was prohibitively expensive for us. So what happened? Well, like some eclipses, this was the day before totality. It was crystal clear. And this is the day of the eclipse. So we were prepared. We had 40-foot waves. Our stabilized platforms were working very well. And at the end we just couldn't see the sun. It was just totally covered. And this is just a beautiful picture showing the Antarctic Peninsula as we approached it on the return. So while it was each eclipse trip ends up being a special, very special experience, one not only for science, but also for exploring the fabric of humanity across the whole world. So for some of the wonders of the universe, I think we should thank the moon and the sun. And the next time you look at the sun, try to imagine its hidden beauty. So I'll stop here.
Thank you so much, Dr. Habbal. That was really wonderful.
Yes, thank you.
So we'll open up for questions now. People are welcome to enter their questions either into the chat box, or you can just unmute your microphone and ask questions directly.
Oh, Rob? Yes, Rob.
Hi, Shadia.
Hello.
I've always wondered, you mentioned the historical observations and the ability to predict eclipses in the thousands of years ago. I've always wondered, how accurately could they predict them? Could they say there was going to be an eclipse in this one city, or was it going to be this one day? Or, how was the timing accuracy?
Okay, so the best example, which I omitted from this this presentation because I was afraid to be going over time, was in so the earlier predictions, they were checked later on when with the more accurate calculations and the bands of totality. Of course, the people would know roughly where they would occur, and so they checked them again, and the difference was, sometimes it was a few years difference. So it wasn't for the locality, the difference was a few years in prediction. So they weren't extremely accurate. But what was interesting is Halley in the 18th century, he was the one known by also a comet is in his name. What he did is, there was an eclipse that was going to go over the southern part of the British island, close to over London, if I remember correctly. So it was a band going over the southern part of the UK. So he had predicted where it was going to be. And what he did is he put out an ad in the newspaper, and he asked people to send him, for those who were in those localities, or if they happened to be, to witness the total solar eclipse, to tell him the time and where they were, to give him their address, actually. And with this information, he managed to to correct the path of totality. It moved just a very little, I mean, just a little bit by maybe a few, less than, I think, 100 kilometers. But it was the first, well, it's a very nice example of one, how the predictions were made at that time, and also of the first examples of citizen science.
Shadia, we have a question in the chat. How
Yes.
about observations from a plane, an airplane? Can you do that?
Okay, so oh yes, you can do them from the plane. The biggest challenge with the plane is that you have several windows. We did try it in 2015, and the result was not very satisfactory. There are people, amateurs, who go on planes and they take pictures. They do see. As an amateur, you only have this one camera and one lens, and you can get, you can have several exposure times. With us, with the colors, we don't have this luxury. First of all, the equipment is much more intricate and more complex. So, but we did try in 2015, and the shaking, even though we had some gimbals, was too much. Our exposure times had to be extremely short. Now, on the vessel this year, we also had, not in 2021, I mean, we're now 2022, we did have 3 different types of stabilized platforms, and all of them worked extremely well. But what we could correct for is we could correct, I mean, there was a drift by more about ±1 diameter of the sun. So we kind of figured it out because we were able to test it before the eclipse. But our colleague Miloslav Drückmüller, but he has the mathematical tools to co-locate all the images, and this was the plan, that all the images would be co-located and added, and then he could produce a composites like the ones you have seen today.
Shadia?
Yes, hi.
A long time ago, when the SST was still in operation, the French ran an eclipse expedition from the SST, and so it could make the eclipse last a lot longer.
Yes, yeah, this is the, interestingly, okay, so they published one result and then they didn't do much more because they recognized that the exhaust from the plane had produced some turbulence in the atmosphere that was impacting their coronal images. So I mean, I know many people take pictures from the plane, but it's, from a scientific point of view, it is not as rich as what we are getting. The ground remains the ideal platform.
We have a couple of questions that came in through the chat. The first one is, can you comment on what happens if, eventually if the sun is diminishing, I guess, over a very long period of time? What do you think an eclipse would look like under that scenario?
Well, first of all, before the sun diminishes and burns, what's going to happen is the distance between the sun, the moon, and the earth is going to change. And it's going to reach a stage where we won't be able to see eclipses anymore. So that's way before, well, I mean, it's also solar eclipses. So, and if once the sun starts to burn, I mean, we won't exist. So we won't be able to see anything. Oh, so one question is, why is the surface of the sun cooler than the corona? Well, that's one of the biggest puzzles we're facing now. And the big scientific question is, not why the surface is cooler, but why is the corona so hot? Because for the surface to cool is kind of natural. You start with a hot interior and the temperature drops with distance from the core. But then what causes the temperature to go up? Now, mind you, in the corona, the density of the matter is much lower than on the surface. So even though it is hotter, it's how should I say? It's not the same type of radiation that you're seeing from the surface of the sun. So we're still trying to explore. I mean, there are lots of theories, and so one is basically what's causing this temperature to rise. And then the other thing is why are there so many different temperatures in the corona? And also from the findings I described today, and I haven't commented too much, is we're able to identify the sources of the solar wind by just latching onto this iron ion. And the question is, what is special about, what is the sun doing to control the temperature of the solar wind to be around 1 million degrees? There's something. So there are several things happening here. There are processes. One is causing the corona to be hot, but there is something else that's controlling this temperature, and not, it just doesn't go above 1.2 million. It's right, the band is very small. And you would say, well, there are other structures in the corona that are at 2, 3, 4 millions, but all these structures remain attached to the sun. Everything that's streaming away continuously is originating from places where the temperature is at the lower limit of 1.2.
Very good. Are there any final questions for Shadia? Okay, well, at this point, I'd like to say thank you so much, Dr. Habbal, for your really wonderful presentation.
Okay, thank you so much for coming.
Thank you very much. Yeah, thank you everybody for coming today. It's great to see you all, and it's really enjoyable to touch base with so many familiar looking faces and names now every month. I'd like to give you a reminder about our next presentation. So it's going to be held on Wednesday, March 23rd at 2 p.m. Hawaiian time. It's going to feature the chair of our chemistry department, Dr. Philip Williams. He's going to be speaking on his research program to do with medicines from the sea. So hopefully we'll see you all there. You can watch your inboxes for invitations to that event. Thanks again, everyone, for coming. I hope you have an enjoyable rest of the day or evening, and we look forward to seeing you soon. Aloha.
Aloha.